I'm writing a game engine to make an open world sandbox game where as much as possible is simulated in real time. Because that sounds like fun. Today we're having a look at super fast UV unwrapping, what that is, and what we needed to do. In order to do basically anything graphically in a 3D engine, you render a lot of triangles on screen and color the area within those triangles in some fancy way, usually texturing, which is fancy speak for there's an image file somewhere that says what that triangle is supposed to look like. Those models and textures are usually made in some fancy program by artists.
I'm not a very good cook.
However, if your game consists of procedurally generated geometry, like a landscape that changes during gameplay, then that cannot be done ahead of time. To understand that entire concept better, let's first have a look at a traditional 3D modeling program and add a monkey. This monkey consists of many triangles. Oh, triangle. Triangulate. Triangle. Now, if we use this monkey in our game as the main character, we wouldn't be particularly happy if the only variety in color it had was one triangle was one color and the other triangle was another color. So we would like to have more variance in color per triangle, which is why we use something called UV unwrapping. You represent every 3D triangle with a 2D triangle in a two-dimensional texture. And the contents of that 2D triangle is basically the contents that you would like to appear texturally on the 3D triangle as well. The positions of those 2D triangles you call texture coordinates. So if we're rendering our lovely monkey, we can just say, oh, which triangle are we rendering? Oh, this one. Okay. What is the color that is stored in my texture, my 2D image, between these three positions? And then basically put that color there. And that's why face. You sometimes see these like horrible looking images online of something in games or whatever, which is just the UV unwrapped face. So how does that work? Step 1 is feeding all of the triangles into UV Unwrapper. Internally it will say, oh, this is the current triangle I was fed. This side in 3D is X long, and this side is whatever long. We'll store like this angle as well, which also makes sense in 3D. And for good measure, I'll also store like this angle. And while we're doing that, we'll also know like, this Mr. Triangle has a friend on the north side that is triangle B, which is basically for each corner of the triangle. We saw I was used in like A, and I was used in A and B. And the triangle shares an edge with another triangle if that triangle appears in 2 of its corners. So we extract all of this generalized information that makes sense in 2D and 3D about this triangle. Step 2. In step 2, we sort all of these triangles by their area in order to be able to start with the largest one. And we basically say, does this fit into our texture? Which in this case, yep, it does. We like know that there's an area in here where this fits into. Now we can say, oh cool, this one fit. What about its neighbors? Does that triangle fit next to it? And it does as well. We'll mark that one. That's part of our cluster as well. And this one, we'll put it here. Then those triangles say, hey, what about my neighbors? Now let's look at this one. Let's assume we would intersect with this one. So we can't place it. So we leave it for later. If they don't fit, they either don't fit because they would like reach outside of the texture, or they don't fit because they would penetrate some other triangle. Then we remove all of the triangles that have been placed, or ignore them going forward, and pick the next largest triangle. Like, this one, and then like we would do that until there's no triangles left. Well, step 4 is actually part of why we made this UV unwrap thing ourselves and didn't just take one off the internets and call it a day. There's a special case of an issue we just glossed over, which is we might not be able to place a triangle next to our existing cluster of triangles because we wouldn't be able to find a space within the texture. Like we wouldn't be able to place this triangle here because it would be penetrated by that thing. What normal texture atlas UV unwrap things do, at least to my knowledge, is they rasterize the triangles into a buffer, which basically means they calculate which pixels will be occupied by this triangle. So they like sort of iterate over the triangle in some fancy way to make sure we are only reaching every pixel once, and then comparing that against some enormous bitmap and doing horrible trial and error things in order to figure out if there's some space where this fits, which isn't necessarily fast because you're rasterizing a triangle, which isn't amazingly fast. And you're trying to find like horrible matches where like there's like a triangle here and it's like, this just about fits somewhere, but like it's really hard to determine where. So this is where we differ and are worse, well, in quality than other texture atlas things. So rather than rasterizing our triangle, we take the bounding box of it, which is the minimum and maximum x and y coordinates in texture coordinate space. And we check if there's some space for that in our texture atlas. And when we expand into our clusters, we simply take the bounding box of the cluster rather than the bounding box of each triangle. If it were checking a bitmap, like the rasterizer checking like every single pixel, does that fit? This would be more expensive because we're actually checking more pixels, but we're not checking a bitmap. That's the second trick. So what are we checking? Let's ask that in a different way. Which operations do we need to perform to sort out the coverage problem? Well, operation number 1 is, hello, I am Mr. Cluster. Is there any room of this size in the texture atlas? So we want to feed the bounding box and it tells us yes or no, we don't have that, and it's at XY position. And number 2, we want to be able to block off the bounding boxes of those triangles, and that's pretty much it. Obviously we could perform them with a bitmap, basically like every pixel is represented with one single bit, but we can also do it in better ways. So what I've chosen to do is a quad tree. A quad tree is a way to divide space. This is our top node, right? We'll draw a little tree on the side to get the tree part and the quad to get... This represents our top node, and apparently it's growing down. This is the root of the tree, and it represents the entire texture. Every node, every one of these, splits into 4 smaller nodes. With my quad tree, that is like that. So that's this one splitting into 4. And then each of those 4 nodes split into 4 nodes. And with every step, space gets divided further and further until you reach 1 pixel. Pew, pew. So let's assume like this size of node, obviously all of those like also have their children and children and children, is actually 1 pixel. So when we would place our cluster or a triangle or whatever the bounding box is, we would cover off some of them in order to say, hey, this is already full. Things aren't as simple for parent nodes though, because let's assume that's 1 and 3, because some of their children may actually be filled and some not. So this node can't tell me I am full or I'm empty, so we need to add a 3rd state they can be in, which is partially filled. So let's pretend we've already placed some triangles in here and they've landed right there. So let's propagate that information to their parents. Let's choose purple for when they've been partially covered. This node here, one high up in the tree, is completely filled. So that's easy. We'll color that blue, which it already is. But this one isn't. There's 2 nodes in here that are filled and 2 that are empty, so we'll color it purple to say it's partially filled. And we'll do that for all of the nodes. Let's, again, abstract that further to their parents. This one is partially filled, this one is partially filled, this one's partially filled, this one's partially filled. And then, eventually, the entire tree is partially filled. With all of that in place, it's obviously very simple to find a free spot. First layer, okay, the tree isn't empty, but there's room here, right? So let's look at its children. So next layer is like, oh, I want to place my thing that's like this big. So the tree goes, okay, does it fit in here? And it's like, nope, wouldn't fit in here. Cool, does it fit in here? Yep. It does. Okay, cool, we've got your spot. So that operation is pretty cheap now. Let's have a look at the other operation that we need to do, which is covering off segments. Now that we've decided to place our new cluster here, we'll just take the bounding box of the entire thing. Let's assume it is here. So we walk down the tree. This one isn't covered, this one isn't covered, but these two rectangles overlap. So that one is interesting, and these two overlap as well, so that one's interesting. We already know that this one's at least partially covered. We also know that they're not fully covered. There's empty space in here, so we need to look further, one layer deeper. We'll cut that into its 4 slices, that one. And now we continue, and we say, what about this one? And fairly straightforward, that one is fully covered, colored blue, and stop. That one as well, no more work to be done here. And there's just these 4 little ones left, so we'll look into them. One layer deeper, that's pretty straightforward. Those two, fully blue, others fully uncovered. That one, this one's fully blue, all of those are fully covered, and the other ones are not touched. I can actually stop checking way high up in the tree. Should be way faster. Step 5. This is fine. Like this works, but it doesn't necessarily produce particularly good results. Obviously, we'll very quickly choose this spot just because they're in the top left corner of a node. But this leaves a lot of unused room around our clusters that would much improve the coverage in the UV map. So rather than placing our orange boxes there, we asked the Quadtree, maybe we could move that entire bounding box top left, which ends up being really straightforward because we're asking our neighbors, are you empty? Are you empty? This one? Oh, that's convenient. I'll move there until we've found a nice spot and we can't move any further to the top left. And that improves coverage massively and isn't particularly expensive. That was fun. How fast is it? This thing is called the Stanford Dragon. It's the 3D scan of an actual dragon, I presume, of a real dragon, obviously, and it is fairly detailed. So I threw that at my UV Unwrap. For doing the entire model, which is 900,000 triangles, with moving to the top left, it took 0.87 seconds, which is about 1 million triangles per second, and without the top lefty party, it's about 2 seconds, which is ridiculous, good enough for like a couple thousand triangles. And a subdivided version of Lucy. Hello, Lucy. That was about 0.02 seconds without moving to top left, and 0.05 seconds or 500,000 triangles per second with moving to the top left. For the Stanford Dragon, the Atlas is pretty much ridiculous. Thousands upon thousands of triangles, and you can somewhat see the tree structure in this. But yeah, this isn't particularly close to the actual use case that we're planning to use it for. I hope that was somewhat coherent. Thank you very much for watching. Consider pressing buttons, and bye!